Today we'll continue communication engineering. This is also applicable for EEE, CSE, ECE, IT. Whereas in ECE you will have communication theory, for EEE and CSE it will be communication engineering, and for IT it is analog and digital communication. This pulse time modulation. Previously we have seen pulse amplitude modulation, and this pulse time modulation is also called as pulse width modulation, or it is also called as pulse duration modulation. This pulse time modulation is classified into pulse width modulation or pulse position modulation. Actually, why it is called as pulse width or pulse position? Because here we used to say the time, that is in the time domain we used to say pulse duration. In the same way we will get changes for width also in the time domain. This is the time domain. We will get both the width as well as duration, because this is called as width and this is called as time. So, and also we can say this, the position has been changed from here to here, isn't it? Here the off time position is changed from here to here. So we can say this as pulse width modulation, pulse position modulation, pulse time modulation, pulse duration modulation. And now these are the types of pulse width modulation, and this is our modulating signal, or we can say this is our original signal or message signal. And what are the types of this pulse width modulation? Listen, this is the peak of the signal. If we have the this is sampling time, this is called as trailing edge. If we take the sampling at the peak of the signal, that is if our on time, that is sampling on time starts here, then it is called as trailing edge. Or if our leading edge, this is called as leading edge pulse width modulation. Why it is called as leading edge? Because our sampling time starts here, isn't it? Here we have sampling time. This is called as trailing edge. If we have sampling time in the middle, and if we have the edges before this middle, then it is called as leading edge. And if we have the sampling time in the middle, then it is called as both edges, that is leading trailing edge. This is called as leading trailing, because here we have leading and here we have trailing. And listen, this is our modulating signal, message signal or original signal. If we take samples in the middle of the signal and if we have the off time after the sampling time, then it is called as trailing edge. And if we have the on time before the sampling time, if the pulse starts before the sampling time duration, then it is called as leading edge of the signal. And if we have sampling time in the middle, if we have the starting time and end time between this leading and that is sampling time, leading and trailing in here, then it is called as both edges, that is leading trailing edge. This is how we can say the types of pulse width modulation. Now let us move on to the generation of pulse width modulation. Listen, this is the PWM generator circuit. This is called as PWM generator circuit. This can be made by using IC555. This is IC555. And here we have trigger input, modulating signal, output, and this modulating signal is given to the control input voltage, because you may know about this IC555 pin configuration. The fifth input we will have this control voltage, whereas this control voltage will be adjusted to 2/3 VCC. So you might have studied about this general pin configuration about this IC555, and in the fifth pin we have control voltage, and this circuit is actually called as monostable multi-vibrator. This circuit is actually called as monostable multi-vibrator circuit. Now, what is multi-vibrator? This is monostable multi-vibrator. What is multi-vibrator? Actually, multi-vibrator, it is an oscillator circuit. Multi-vibrator is said to be, it is an oscillator which produces non-sinusoidal signal. So, this multi-vibrator means that is a oscillator. Actually, that is an oscillator and that will produce non-sinusoidal signal. For example, square wave, because it is non-sinusoidal signal. Now, what is monostable multi-vibrator? What is mono? So, mono means single. So it has only one stable state and another one is quasi-stable state. So it may be either stable or unstable. That is called as mono. So if it is mono-stable state, we can say that it has one stable state and one quasi-stable state. And this circuit will be useful for generating single output pulses. This monostable multi-vibrator circuit is useful for producing single output pulse which has adjustable time duration. So if we have timing here, then we can get next pulses here. So it will produce the single output pulses of which has adjustable pulse duration with response to this trigger signal. So how can we get this changes in the width? That is by response to this trigger signal. That is called as monostable multi-vibrator. And we are saying that we have changes in the width of the signal, isn't it? So we can have changes like this, or we can have changes like this. The width may increase or decrease. That increase or decrease depends on the external components connected to the circuit. Now what are the external components connected to the circuit? R, C. So based on this R and C, the width of the duration of the pulses may change. Now this is a PWM generation. This is pulse width modulation generation circuit, and this is actually monostable multi-vibrator. What is a multi-vibrator? It is a circuit that produces non-sinusoidal signal. Now this will produce square wave because this is a non-sinusoidal signal. Now what is this monostable multi-vibrator? Mono means it has only one stable state, and another, what about another state? That is quasi-state. So it may be either stable or unstable. And now what is the function of this monostable multi-vibrator? This monostable multi-vibrator will produce output pulses of adjustable width. So this will produce output pulses of adjustable width. So that is the reason why we are using this monostable multi-vibrator for generating PWM. Now we are saying that the width may either increase or decrease. How can we say that it either increases or decreases? That is based on the external components connected to the circuit. Now what are the external components connected here? That is R, resistor, capacitor. So if you increase or decrease the values of this resistor and capacitor, we will get the difference in the duration of the pulses. So this is how the circuit works here. Now let us move on to the working of this. So how the circuit will work? Now already I said the fifth pin, that is if we see this pin configuration of IC555, in the fifth pin we have control voltage, and initially, that is internally, it is adjusted to 2/3 VCC. This control voltage is internally controlled by to 2/3 VCC. Now what happens? We are giving modulating signal here. So due to this modulating input, what happens? This will change the control voltage. So previously it was initially adjusted to 2/3 VCC, but what happens? Externally we are giving modulating signal to the input phi. Now this modulating signal will change this control voltage. So 2/3 VCC, this will be changed by this modulating signal. Therefore, if this modulating signal changes, what happens? Automatically it will change the threshold voltage. So it will automatically change the threshold voltage level of this circuit. Now what happens? So due to these changes, the period will change. That is the charging and discharging period. The charging of capacitor will change, isn't it? So if the charging of this capacitor changes, so that we'll get changes, we'll get the changes in the output of the pulses. So this is the concept of this PWM generator. Now this is a monostable multi-vibrator and it produces square wave. And listen, here we have control voltage. Initially it is adjusted to 2/3 VCC. Now what happens? We are giving externally modulating signal. Now this modulating signal will change the 2/3 VCC voltage. So if this changes, what happens? Internally the threshold voltage will change. The circuit's threshold voltage will change automatically. If the threshold voltage changes, what happens? That will change the charging time period of the capacitor. If the charging time period of the capacitor changes, what happens? That it automatically changes the width of this pulses. That is how pulse width modulation is done here. See here we have a trigger input. So here we have a trigger input pulses. This is also to be pulses. Here we are giving trigger input as pulses. And here we have modulating signal. These two signals are given externally. Trigger input, modulating signal. Now what happens? So due to this entire process, we'll have changes in the width of the signal. So that we'll get pulse width modulation output. This is called as pulse width modulator generator. Now let us move on to the demodulator. Listen here, this is demodulation of PWM signal. Now what will be the input of this demodulator circuit, which we have transmitted here? In the modulator, that is in the transmitter we have modulator, in the receiver we have demodulator. Now we have transmitted the signal, isn't it? This modulated output will be transmitted via channel and it will be received by the receiver. Now this demodulator will receive the information which we have transmitted. Now here we have, just a minute. This is how we'll get the output for this. Listen, here we have symmetrical, isn't it? So before that, what happens? We are going to receive the signal which we have transmitted in the transmitter. So we have transmitted a signal. Now that signal will be received here. So after receiving, what happens actually, previously the input signal which we have transmitted will receive the signal, but will receive the signal with noise, so that here noise are present in the signal, but we have received the information which we have transmitted. Since it has undergone many processes, as well as since it passed through the channel, there some of the frequencies will get mixed with our original frequency. So what happens, we will receive the information, but here see here some noises are present. So what happens, this signal is given as input to the symmetry trigger. So what is the function of a symmetry trigger? This is our symmetry trigger. Now what is the function of a symmetry trigger? This is said to be a pulse shaping network. So this will shape the pulses. So here see noises are absent now. So here we have the received information, and this information, that is this signal, is given as input to the symmetry trigger. Now what is the function of a symmetry trigger? Actually this is called as pulse shaping network. So this will shape the pulses so that we will get the flat pulses and noises are removed here. Then this output is given to the ramp generator. Now we know if it is a ramp generator, it will generate the ramp signals. So listen here, here we have ramp generator that will produce the ramp signals. So how it will generate the ramp signals? Here we have the start time, that is on time, that is charging of the capacitor, and during off time of pulses, then it remains constant. Again it goes down, that is during starting of the signal it goes down. Again then for the on time it turns on. During off time remains same. Then again during on time starts, then it moves to stable state. Then because it is a ramp generator, so this will produce ramp signals. Now listen here, based on the width of the signal, our width changes. See here, based on this width our signal changes. So based on this width our height of the signal as well as this width changes. So here this is called as ramp output. So here we had input signal, symmetry trigger, that is pulse shaping network. Then this output is given to the ramp generator. Now this has produced ramp signal. Now this is given to the adder circuit. So if it is adder, it must have two input, that is more than one input where it has to add the signals. Another input is given from the synchronization pulse generator. This adder will have this ramp as well as synchronization pulse generator output. Listen here, this is our synchronization pulses. So what is the mean by the synchronization pulse generator? This will produce a train of pulses, that is it will produce pulses here. So this is output of the synchronization pulse generator. So this will generate the train of pulses. And now here we have a adder circuit. What is the function of this adder? This will add this ramp generator output as well as the output from the synchronization pulse generator. And now these two signals are added here. See, this is our ramp output. Is it visible? Yeah. This is our ramp output. This is our synchronization pulses. So these two signals are added here. This is the output of the adder. These two signals are added here. Now the adder output is given to the level shifter. Now what happens, what is the function of a shifter? This shifter will shift the signal. So this will shift the signal, that is it will shift the signal. See here, either we can use positive shifter or negative shifter. So what we did is, it has shifted 0 line below. See here, it has shifted this ramp. Here we have adder output, and here this is the output of level shifter. This has shifted to below the 0 line. So this has shifted below this line. This is the output of the level shifter. Now this shifter output is given to the rectifier circuit, that is clipper circuit. Now what is the function of a clipper? It will clip the either positive or negative based on the circuit which we are using. If you use positive clipper circuit, then it will cut the positive off of the signal. If you use the negative clipper circuit, then it will clip, that is it will cut the negative off of the signal. So what happens here, we are using this clipper circuit so that it cuts the signal below this 0. So it cuts the negative part of the signal. So we will get only this signal, positive signal. Then what happens, this output is given to the low pass filter. Now what is the function of a low pass filter? This low pass filter will allow only the low frequency of the signal, and it what happens, the high frequency signal, then it will be blocked by this low pass filter. It will be filtered, so only low frequency signal will be allowed. So finally we will get the signal like this, that is our demodulated output. So finally we will get the signal like this, but actually this is not in the proper shape. So finally we will get to the shaping network, so that we will get the same signal which we have transmitted in the transmitter. Now listen, this is the input signal which we have received from the Schmitt trigger. So from the Schmitt trigger, this is actually block diagram for demodulation of pulse width modulation. So the signal which we have transmitted, we are going to receive the signal in the receiver. So what happens here, we have noises in the signal. So by giving this signal to the Schmitt trigger, then it will be shaped so that you will get proper signal. Then this output is given to the ramp generator. The ramp generator will produce ramp signal. So based on this width, the signal will be produced. Then again here we have a trigger input that is given to the synchronization pulse generator. So based on this trigger input, we will get the output, that is train of pulses. It will produce train of pulses. These two are added in the adder, then it is given to the level shifter. This level shifter will shift the signal either above the 0 line or below the 0 line. Then this output is given to the rectifier circuit, that is a clipper circuit. So if you use positive clipper, it will clip the positive of the signal, and if we use the negative clipper, then it will clip the negative of the signal. And finally the output is given to the low pass filter, because we have unwanted frequencies, high frequencies. Why we are using this LPF? Why don't we use this HPF? Because the signal which we are transmitting in the transmitter is always a low frequency signal, whereas the carrier will be always a high frequency signal, which I said earlier in my previous classes. So that is the reason why we are using this low pass filter here. Why don't we use this high pass filter? Because our original signal is always a low frequency signal. So we have to filter only that low frequency signal by blocking that high frequency signal. So that we are using this low pass filter, and finally you will get the demodulated output. This is what we have said here. So that is the output is of the transmitter is given to the Schmitt trigger. This is our signal. It is given to the Schmitt trigger. So Schmitt trigger makes the signal shape perfectly. Then the output is given to the ramp generator. So here we have a off state, and this is our on state. So off state. So based on this, with the duration changes, and here we have synchronization pulses. So it will produce a train of pulses from the trigger input. Now what happens, these two will be added in the adder. Now what happens, then the next one is level shifter, so that it will shift the level. Then we have a rectifier, so it will clip the circuit, because here we are using clipper circuit, so it will cut, that is cut. Clipper will cut the signal, unwanted signals, and finally you'll get the output, that is from the LPF. This is all about generation and reduction of pulse width modulation. Hope you understand. We'll meet in the next video. Thank you.